Welcome to the October 2021 Eastside Clinic. I'm Alex Brickhoff, and I'll be your host tonight. Our clinic tonight is hosted, as usual, by the 4th Division of the Pacific Northwest region of the National Model Railroad Association. Tonight, Dan Kellogg is here to talk to us about a new strategy for representing signals on the model railroad. And Dan will be presenting his thoughts and application methods on a new signaling system that has been developed by Model Train Technology. Let me turn the floor over to Dan Kellogg. And Dan, if you're ready.
My interest in model railroading started after I worked for the Great Northern Railway and the King Street Terminal Company as a relief operator during my college years. My principal station was the interlocking towers at North Portal and South Portal on the Seattle Tunnel near King Street Station in Seattle. For 45 years, I was an armchair model railroader. But for the last 5 years, I have been actively constructing an N-scale layout in a 10 by 10 bedroom in my house. As Alex stated, tonight's clinic is titled A New Strategy to Represent Signals on a Model Railroad. I intend to share news of a new signaling system that has been developed by Model Train Technology of Orlando, Florida. They have developed a trackside precision detector that detects the presence of a train on an adjacent track without the use of traditional track detection circuits, infrared light, computer programming, or even soldering. Their signal controller takes the input from the detector and displays the appropriate aspect on the signal. I'm going to use a PowerPoint presentation to briefly describe the traditional signaling applications and then to describe the new system. Then I will present 2 short videos. The first will feature a small signaling module that I built to demonstrate the system, and the second video will show a short tour of my layout under construction and then focus on the Model Train Technology signaling system in operation at the most recent module that I constructed on my layout at East Skykomish. I always expected that my model railroad layout would have signals that were generally prototypical. In fact, the first section of track that I ever installed had signals. They just didn't work. They were always red because my signal had no logical interface between my train detection devices and the signals. In fact, this is what the wiring for the signals looks like underneath the layout. I even went to 2 NMRA conventions to find a signaling system that I could understand and operate, but each system required some form of train detection and computer program to logically drive the signals. And since I'm not very comfortable with electronics, much less computer programming, my layout still waits for its signals. So here's the problem. This is what you need. A signaling system needs 3 things. Number 1, sensors to detect the presence of a train in a block of track. Number 2, a system that will logically determine what to do with the input from the sensors. And number 3, an appropriate electronic signals to display the logical output from the system. So the train detection device could be a current detection device like the NCE BD20 that most of us are familiar with. It could also be a reed switch or infrared lights, but ambient light is always a problem. The logical interface that you need has to do with microprocessor chip devices or layout command control systems or computer programs like JMRI or CMRI, but all require programming to use the sensor input to drive the track signals. This is a simple example of the logic that's needed for signal operation. If a train is approaching block A, is in block A and is approaching the signal at block B, if block B is clear and if block C is clear, then the signal at block B will be green. If block B is clear and block C is occupied, then the signal at block B will be yellow. And if block B is occupied, then the signal at block B will be red. That's pretty simple, but things get complicated. Trains come from other directions. You have diverging routes or crossover tracks to take into account, and some railroads even use signals to give speed instructions. So this is the simple strategy that I had hoped to use. On a 3-light signal, if the top light is green, that means proceed because 3 blocks ahead are clear. If the middle light is flashing yellow, that means to approach because 2 blocks ahead are clear. If the middle light is solid yellow, you can approach, but only 1 block ahead is clear. And if the lower light is red, you have to stop because the block ahead is occupied. But all of that requires logic. Model Train Technology of Orlando, Florida has developed a new train detection and signal control system that provides an animated signal system that represents signals in a model railroad operation. The components of the system are 4. The first component is the power module that provides power to all of the components. The second component is the precision detector itself that sits alongside the track and detects the presence of a train passing the sensor by an electronic beam. The third part is the signal controller. This is the brains of the operation. This receives the input from the precision detector and provides the logic to drive the signals. And then the fourth thing you need are signals, either LED or fiber optic signals to display the appropriate signals. This is a photograph of the power module. It has 10 terminal pairs that can be daisy chained. It provides 5-volt DC power and has a very interesting magnetic base that allows you to hold the power module in place and yet remove it from the magnetic base to work on it. This is the eyes of the system. This is the precision detector. The 2 photographs on the right show the circuit boards that give the instructions. And up in the upper right-hand corner, this is the actual detector that emits the beam that is interrupted by the train passing by the sensor. And these sensor boards are hidden inside of this cabinet on the left, showing the front and the back of the cabinet. And in end scale, about half of this circuit board is underneath the surface of the layout. It has a special holder for it. And this is the window that the detector peeks out of to emit the electronic beam. So the detector device is hidden in a trackside cabinet that looks very much like an electrical cabinet. The beam range is adjustable from about 1/2 inch to about 5 3/4 inches. As Alex said, you can use it in N or HO or O scale and determine and set it for the width of the track that you want it to sense. And the signal timing can be adjusted from 0 to 60 seconds. This is the signal controller. This is the brains of the operation. And there are 2 different signal controllers, one for LED lights and one for fiber optic lights. It can be powered and controlled by a DCC system. And this, so the detection circuit comes in at this terminal. We'll talk about the latching circuit later. This is the power that comes in from the power module. And these, in this case, this is a fiber optic signal controller. So the fiber optic cables are going out on the right side. And this is the signal that Model Train Technologies makes available. There are 2 different kinds. One is for LED lights, one is for fiber optic lights. This happens to be the fiber optic light, and you can see the fiber optic cable coming in at the bottom and then the fiber optic cable, or the fiber optic light, is actually white, but the lens in the signal is green or red or yellow, as the case may be. So how does the system work? The default signal color is green. When a train triggers the precision detector, the signal turns red. When the train is past the detector and after the signal delay that you would set, the signal cycles from red to yellow or flashing yellow and back to green. And the signal controller has 9 possible settings for the pattern of the signal. The latching feature that I mentioned before allows the signal ahead, in the block ahead, to delay the signal on the signal behind. So if a train triggers the precision detector in the first block, the signal on the first block turns red. And if the train then triggers the precision detector on the second block, the signal on the second block turns red, and the signal on the first block doesn't cycle completely back to green until the second block is clear. So model train, as you will see, model train technology system is not at all prototypically correct in many respects, but it is a very good representation and animation of signals for a model railroad layout. Used with the signal cycle timing and the latching features, it will represent an authentic signal system on a model railroad. And the good news is it does not require computer programming. So these are some of the resources that I have discovered. Burr put on an excellent clinic for the railway modelers meet last May on the basics of signaling. There's a new book from David Abeles that has just been published on a guide to signals and interlockings, and a recent article in Model Railroader magazine. All of these articles, I believe, were published before the model train technology system was made public late in the spring. And so they don't really deal with the system. You're hearing about something that is very, very new and hopefully very useful. This is the video that I created to illustrate the components of the model train technology signaling system. My name is Dan Kellogg. I am building an N-scale model railroad in my home. My layout will represent the modern operations of the Burlington Northern Santa Fe Railway. It will operate in 3 subdivisions from Seattle north to Bellingham and east to the Cascade Tunnel. I always envisioned that my layout would include block signals. In fact, I installed signals on the first section of track that I ever laid. However, those signals always display a red aspect because I have never been able to find a signaling system that does not require computer programming in order to provide the logic to drive the signals. But now I believe I have found a reasonable solution that provides signal animation relating to the movement of trains, but does not require computer programming. The solution has been developed by Model Train Technology of Orlando, Florida. This system is certainly not a prototypical system of signals like you would find on an operating railroad. Let me give you just a couple of examples. Prototype signals on an actual railroad default to a red aspect and then cycle back to yellow and to green under positive control by a dispatcher or interlocking operator. But the model train technology system defaults to green when the signal sensor is clear. It then triggers a red aspect when the signal sensor senses that a train is on the track adjacent to the sensor. Then, when the sensor is cleared, the system automatically cycles from red to yellow and finally back to green. Another example is the sensor does not protect an occupied block. If a train passes a sensor at the beginning of a block and proceeds into the block and clears the sensor just senses the presence of the train while the train is adjacent to the sensor and triggers the signal aspect to red, but only so long as the sensor is activated. Once the sensor is cleared and the train has occupied the block, the signal cycles back to yellow and finally to green, subject to the adjustable timing mechanism. But while the train is still occupying the block, the signal can cycle back to green even though the train is still occupying the block that is supposedly protected by the signal. But despite the ways in which this system is not prototypical, it still is a very good system to represent operating signals on a model railroad. When a train passes the sensor, the signal light turns red. When the train clears the sensor, the signal light cycles back to yellow and finally to green. In this way, it is an excellent system to animate signal operation on a model railroad. I built this demonstration module for two reasons. Number one, I wanted to prove to myself that I could install the system. Number two, I wanted to have a way to demonstrate how the system is installed and operated. So let's take a look at the components of the demonstration module. This is the layout surface. The horizontal surface obviously represents the top surface of the layout with the track installed. The system components on this surface would typically be visible on an actual layout. The layout surface is divided into two blocks, Block A and Block B. Signals are located at the beginning of each block. The vertical backboard represents the underside of the layout. The system components on this surface would typically not be visible on an actual layout. The power module provides 5-volt DC power to all of the system components. This power module is sold by Model Train Technology, but other power sources from 5 to 12 volt DC could be used. This is the precision detector that has been developed by Model Train Technology. It's concealed in a trackside electrical cabinet. It emits an electronic beam that can be adjusted between 5 millimeters and 150 millimeters, which is roughly 1/2 inch to 5.75 inches. When the beam is interrupted, the sensor sends a signal to the signal controller and changes the signal aspect to red. When the signal is cleared, then the signal turns back from red to yellow to flashing yellow and to green. The sensor can be set for N scale, HO scale, or O scale layouts. This can limit the depth of the signal to the width of the track. The recommended voltage for the precision detector is 5 volts DC, but it can run on 12 volts DC. This is the signal controller. This is the brains of the operation. The signal controller receives the input from the precision detector and changes the aspect of the signals accordingly. The recommended voltage for the signal controller is also 5 volts DC, but it can also run on 12 volts DC. There are two types of signal controllers. One type powers LED signal lights. The other type uses fiber optic cable to light the signal lights. The signal controller on my demonstration module is for fiber optic lights. The LED signal can also switch between common anode and common cathode. Either type of signal controller can be powered and controlled via DCC. This is the signal that has been developed by Model Train Technology. The signals can be LED lights or be lighted by fiber optic cable. The signals on my demonstration module are fiber optic lights. The light emitted by the signal controller is white. The lenses on the signal lights are colored red, yellow, or green. The signal at block A is green, indicating that block A is unoccupied. But when the train approaches block A, it passes by the precision detector and interrupts the beam. The signal aspect on the signal for block A immediately turns from green to red. When the train clears the signal aspect on the signal for block A cycles back from red to yellow to flashing yellow and back to green. I have chosen on this signal to include the flashing yellow cycle because it is prototypical on the BNSF. The length of each cycle can be extended to up to 60 seconds. A train on the adjacent track will not trigger the sensor at block A because the sensor has been set to detect only trains on the nearer track. But if the train proceeds to block B, it will trigger the sensor at block B because that sensor is set to detect trains on either track. The signal controller can be adjusted to create 9 different patterns for signal colors and cycles. I have the signal controller at block A set for option 4, which cycles the signal color from red to yellow to flashing yellow and back to green. The signal controller at block B is set for option 3, which omits the flashing yellow cycle. This adjustment is done by pressing the button on the front of the signal controller. The timing of the length of the cycle can also be adjusted by a potentiometer on the front of the signal controller. The signal controller has a latching circuit which can be used to keep one block signal from cycling back to green until the train has cleared the precision detector at the following block. Each signal controller has a latching terminal, so a wire can be connected from one signal controller to the latching terminal on the next following signal controller. The purpose of that connection is to allow the signal at the first block to be controlled by the signal controller at the following block. This is what is meant by latching. If a latching circuit is connected between the signal controllers for blocks A and B, for example, if a train passes the precision detector at block A, it will trigger the signal controller at block A and turn the signal at block A to red. When the train clears the sensor, the signal aspect at block A will cycle from red to yellow or flashing yellow. But if the train proceeds to pass the precision detector at block B, it will trigger the signal controller at block B and turn the signal at block B to red. But until the train clears the precision detector at block B, the signal at block A will not cycle back to green. It will remain at its aspect just before green until the train clears the precision detector at block B. Then the signal at block A will immediately cycle to green. This latching circuit improves the realism of the appearance of the signaling system because it appears that the signal at block A is protecting block A until the sensor is cleared at block B. I recognize that this system for animation of model railroad signals will not satisfy every modeler. For those who have an interest in prototypically correct signals and who have the resources and skills to program the logic required, there are other better systems available. But for someone like myself who does not have the ability or interest to learn to program the signal patterns and who is satisfied with the animation of the signals in a somewhat realistic fashion, this new detection and signaling system from Model Train Technology is worthy of consideration. The system can be adapted to drive crossing signals and can trigger but not power relays to initiate other actions. It is very fast and easy to install. The wiring requirements are very minimal and no soldering is required. The operations manual provided is very clear, and the support staff at Model Train Technology is very patient and helpful. I'm very pleased to have discovered the train detection and signal system by Model Train Technology as a practical and realistic animation system for the signals on my model railroad. Some of you have been wondering what I have been doing in my layout room for the past 5 years. So I thought I would take this opportunity to share a short video tour of my layout under construction. After the layout tour, the video will focus on the Model Train Technology signaling system in operation on the 3rd level of my layout at East Skykomish. I'm modeling the Northwest Division of the Burlington Northern Santa Fe Railway in N scale in 3 subdivisions as a point-to-point layout with loops on each end to enable continuous running on double-track main lines. Each subdivision is constructed on one of 3 shelves around the room with a peninsula in the center of the room on the 2 lower levels. A helix will provide connection between levels 1 and 2 and levels 2 and 3. A 3-level swing gate provides access to the layout room. When closed, the swing gate allows trains to operate across the door opening on all 3 levels simultaneously. I am modeling the BNSF in modern equipment and operations with the notable exception of the interlocking tower at North Portal. My model style is semi-freelance. I'm freely picking and choosing the extent to which I can afford the time and effort to replicate the scenery, structures, and operations of the prototype. Let's take a brief video tour of my layout before we focus our attention on the Model Train Technology precision detector signaling system that I have installed in the module at East Skykomish on level 3. BNSF 9959 with a small cut of cars is emerging on the northbound main line out of the Seattle Tunnel at North Portal on level 1, which is the Seattle subdivision. As the train proceeds north, it passes the yard office and car shop and proceeds through the yard. The train passes the engine servicing facility and then exits the yard. The train passes over the swing gate and my representation of bridge number 4 and proceeds briefly along the shoreline of Puget Sound before entering the helix entrance to level 2. This is level 2, the Bellingham subdivision. None of the track work or scenery has been installed on level 2. Right now, level 2 is essentially filled with construction materials and tools for my construction of level 3. This is the entrance from the helix to level 3, the scenic subdivision. The double-track main line will proceed over the swing gate and a bridge over the Skykomish River. The tracks will follow the river and enter the little town of Skykomish where 4 signals have been installed at East Skykomish. The tracks will then proceed out of Skykomish, across a little creek, and up to the Cascade Tunnel entrance. Now I'd like to show the model train technology signal system in operation. 2 signals control eastbound and westbound movements on each main line. At East Skykomish, each main line has a turnout to a passing siding. The signals do not differentiate between movements on the main lines and movements to or from the main lines to the passing sidings. The model train technology signaling system simply senses trains as they pass the precision detector without regard to whether the train is proceeding on the main line or over the turnout onto the siding. This is not prototypical. The system is better described as an animation or representation of an operating signaling system. Between the signal masts on each side of the main lines are 2 boxes which appear to be electrical cabinets for the signals. Each box contains a precision detector which has a sensor to sense the presence of a train on the adjacent track but not on the other track. The signal aspect is normally green when no train is passing the sensor. This is also not prototypical. A prototypical signaling system would default to a red aspect or perhaps a dark aspect if no traffic was anticipated. As a train approaches the sensor, the signal aspect is green. But when the sensor senses the presence of the train adjacent to the sensor signals the signal controller, and the signal controller turns the signal aspect to red. This represents a realistic animation of the signal. So long as the train is adjacent to the sensor, the signal aspect will remain red, which is prototypically correct. But when the train clears the sensor, the signal controller starts a time delay before changing the signal aspect from red to yellow, and in my operation to flashing yellow, and finally back to green. I've set the signal controller for a 30-second time delay for each change of the signal aspect. This is not prototypical. The change in signal aspect from red back to green occurs whether the train is still occupying the block supposedly controlled by the signal. The change of signal aspect is determined by the fact that the train has cleared the sensor without regard to whether the train has actually cleared the block. Model train technology has a system called latching, in which signals on adjacent blocks can be connected so that the signal at the first block will not turn back to green until the train has cleared the sensor at the following block. I intend to include latching in my signal installation because it will improve the animation of the signals, but I have not yet installed the latching circuits at East Skykomish. To summarize, we have seen the signal with a green aspect before the train passed the precision detector. As the sensor sensed the presence of the train, the signal controller turned the signal aspect from green to red. The signal aspect remained red so long as the sensor sensed the presence of the train. When the train passed the sensor, the signal aspect turned from red to yellow, and then to flashing yellow, and finally back to green with a 30-second time delay for each change of the signal aspect. That is the essence of the model train technology signaling system. While the system is not prototypically correct in several respects, it is a realistic animation and representation of signals on a model railroad. The model train technology signaling system will not appeal to all model railroaders. For those with an interest and ability to program signal operations on a computer, there are other systems which will be much more satisfactory as a prototypical approach to signal operations. But for someone like me, with limited interest and ability to program signal operations, the model train technology signaling system is a very credible animation and representation of railroad signals, and the system is relatively easy to install. All right, Alex, that concludes my presentation. I'll be glad to answer any questions. I'll try to answer any questions.
Okay, thank you, Dan. That was a very informative clinic, and I'm sure there are probably at least a few questions or comments out there.
I have one, Smokes. You had the train or the locomotive running through the signaling in one direction. What happens if you back up?
It would trigger the signaling system again. The system is not prototypical in that respect. It simply is an electronic beam, and once the electronic beam is interrupted, it will change the signal aspect.
So if in the one you just showed, the locomotive had backed up while the signal was still on yellow or whatever, would it just go back to red?
I believe so.
Because it presumably does not know what direction the train's going.
That's correct. It simply knows that the train is adjacent.
Okay, so if you were running, I don't know if there's a right or a wrong track on that, or they're interchangeable. The way it's signaled, it looks like it can run either way on either track.
Correct.
What is happening to the back-to-back signal when you go through one? You've got two signals there allowing bidirectional running. So when you go through the one you showed, what happens to the one that's on the other side of the gear, facing the other direction on the track?
Max, I don't know that there would be any effect, but I'm not familiar enough to give you a definitive answer. My guess would be that it would not affect the second signal, because the second signal is going to be controlled by what it senses is passing the second signal.
Yeah, but you only had one sensor block, right? One
Yes,
dummy cabinet, if you like.
that's right. In my presentation tonight, I did not have the latching feature installed to be able to show what happens from one signal to the next signal.
Okay.
We do have one request. Somebody wrote into the chat at the bottom that asking Dan if we could see the contact info for MTT again, please.
Yeah, modeltraintechnology.com.
So Dan, I have a question for you. One thing that I always look at when I compare systems like this is the price. Do they have various entry-level packages or intermediate level packages, or what would you say is a ballpark price for a system like what you've demonstrated?
Yes, I took a look at their website. They have a store of all of their products, because they have a lot of other products other than the signaling ones. But they have a starter kit which includes the one of the power modules, one signal controller, one precision detector, and that is about $100. The price depends upon what gauge, whether it's N scale or HO or O. The other the pieces by themselves, the power module is, I would say, an average of about $45, and the precision detector, which is the little item that's inside the signal cabinet that senses the train, that's probably an average of about $33. And the block signals that actually show the signals, the fiber optic ones, are an average of about $25.
Yeah, I got a question for you, Dan. One great presentation, very nice layout coming along, and the signaling thing is really cool because I'm like you. I want to see the signals, but I don't have all the technology or the know about or want to figure out the prototypical signals. My question would be is, can you use searchlight signals with that system as opposed to the 3 separate bulb system?
Yes, the model train technology has several different types of signals. And for example, I'm pretty sure they have Pennsylvania Railroad signals. You should look at their website and look at their store, but I think you'll find what you're looking for.
Okay. And then is it possible to use another brand of signal such as a Tomar or an Atlas signal as well too, or is it specifically set up to use their signals?
So you'd be using an LED type of signal? Yeah, they support the LEDs, and you should definitely check with them. But I'm quite certain that you'll be able to use your existing signals, because as I said, they will go either with common anode or common cathode. So they're really trying to be very accommodating.
Dan,
Yes.
do you actually know what the detection sensor is? Is it
No.
infrared? Is it infrared?
No, I asked the inventor and he declined to describe it other than an electronic beam.
So that's probably infrared.
I've been experimenting with a device called a Time-of-Flight detector. And from what I've read on the model train technology on the way their precision detector works, I believe that is what they're using, because what the time-of-flight detector actually does is it emits an infrared laser beam, and then it measures the time it takes for that beam to be reflected, and by measuring the time, then it can compute the actual distance that the object is from the device, from the detector. So when you adjust it for your track, like you've got it looking across 2 tracks, it's distinguishing the distance. If you change the setting, you could conceivably detect the train on the other track also. So anyhow, that's what I believe the technology is the time-of-flight detectors. And they are infrared light, and they are almost completely impervious to ambient light. I've shined my little flashlight directly on them, and the reading I get out doesn't even waver. And it seems to be relatively insensitive to the color. The difference between a dark freight car red or brown, or even a white reefer, it seems to respond pretty much the same. I have several of them in use on my layout right now. Anyhow, that's what I believe the technology is and how it works.
I have one question here. So they only showed 2 of those light emitters or whatever. Could you daisy chain them up to multiples besides just 2? So you could, bring it on further down if you had passings or other things that you wanted to know where the train was.
I think that question would be better posed to Jim Lewis of Model Train Technology.
You never tried it, right?
I have not tried that, no.
Okay, thank you, Dan. That was a very informative clinic.